Hello, this is part 2, the second video of looking at rules for assigning oxidation numbers, in which we're going to look at a number of examples applying the rules that were discussed in the first video. So if you haven't watched that video yet, please do so. The first set of examples we want to do involve the calculation of the oxidation number of nitrogen in the following compounds or species. So the first one we're going to look at is the nitrite ion. And so in these, what we're going to do is look at the atoms other than nitrogen and see what we know about them and determine what the oxidation numbers are in those atoms, and then calculate what the resulting oxidation number of nitrogen must be. So nitrite is a polyatomic ion, and couple rules apply here. One is the sum of the oxidation numbers in a polyatomic ion has to equal the charge on the ion. So when we add up all the oxidation numbers, they have to add up, in this instance, to -1. So we start out with the oxygen. Oxygen usually, almost always, is -2. And so if oxygen is -2, 2 times -2 is -4. And we want to find out what nitrogen is to overall give us the charge of -1. So 2 times -2 is -4, plus whatever the oxidation number of nitrogen is -1. And so if we just do some algebra there, that tells us the oxidation number on nitrogen has to be +3. H2N2, or N2H2, is written here. Hydrogen with a nonmetal is +1. We've got 2 of those. We're trying to find out what each nitrogen is to give us an overall sum of 0, because now we're using the rule where the sum of the oxidation numbers in a neutral compound has to equal to 0. So if each hydrogen is +1, I've got +2, plus 2 nitrogens gives me 0. That means the 2 nitrogens have to add up to -2, and each nitrogen will have an oxidation number of -1. N2O, dinitrogen monoxide. Oxygen is -2, plus I have 2 nitrogens, and they all have to add up to 0. So 2 nitrogens, each one of those will wind up being +1 for the oxidation number. Not a charge. These are molecular species, molecular compounds. The atoms don't have charges in them, but we can't assign oxidation numbers. N2O4, dinitrogen tetroxide. Oxygen, -2, plus 2 nitrogens. They all have to sum to 0. So 4 times 2 is -8. And that has to equal to what the sum of the 2 nitrogens is. So in this instance, nitrogen has a +4 oxidation number. So -8 divided -2 is equal to n if you want to do it algebraically. You might be able to do it in your head, and that's fine too. The next one, nitric acid. Hydrogen with a bunch of nonmetals is going to be +1. Don't know what the nitrogen is. And I've got 3 oxygens, each worth -2. And they all have to add up to 0. So 3 times 2 is -6, plus 1 is 5. So n plus 5 is equal to -5, excuse me. 3 times -2 is -6, plus 1 is -5. So n minus 5 has to equal to 0, and so n is equal to 5. The oxidation number on nitrogen here is +5. Calcium nitride. Calcium is a group 2 alkaline earth metal, so this is actually an ionic compound. Each of those calciums have a +2 charge. So in all, I've got +6. The nitrogen has to have a negative charge. It's an ion, and so they have to all add up to -6 to balance out the +6. So each nitrogen in calcium nitride is -3, which is something we would suspect anyway if we looked at the periodic table, with nitrogen being in group 5A. In an ionic compound, it wants to gain 3 electrons to get a noble gas configuration like neon. And so the nitride ion has a -3 charge, nitride. But we've just re-emphasized that doing this oxidation number calculation. N2, diatomic molecular nitrogen. It's an element by itself in its free state. By definition, its oxidation number is 0. N3-, the azide ion. The sum of the oxidation numbers of polyatomic ion has to equal to -1. And so we've got 3 nitrogens. And so each nitrogen here is -1/3. -1/3. So if you watch the previous video, we said that oxidation numbers can be either positive or negative. They can be integers or fractions. And lo and behold, here we have an oxidation number that's actually a fraction. It's -1/3. No real physical significance. Each of those individual nitrogens don't have a charge, but that species as a whole does have a charge because we've added 1 extra electron into it. Number 2, let's calculate the oxidation number on oxygen in each of the following compounds. So the first one, O2, diatomic molecular oxygen, is an element in standard state or free state. By definition, each of those oxygens has an oxidation number of 0. H2O, everything's a nonmetal. We'll refer back to the rules. I said that hydrogen with a nonmetal, here oxygen, has a +1 charge. So I've got 2 of those, plus my oxygen has to equal 0. The sum of the oxidation numbers in a compound has to equal 0. And so my oxidation number on oxygen is going to be -2. And so we can almost refer back to the rule that says oxygen usually or almost always is -2, and that's what it works here. Example 2C gives us the first example where oxygen isn't -2. So each hydrogen here still is +1, but now I've got 2 oxygens that have to add up. Everything has to add up now to 0. So 2 times +1 is +2, plus my 2 oxygens is equal to 0. My 2 oxygens now have to add up to -2. So each individual oxygen is -1. So here oxygen does not have a -2 oxidation number, it's -1. And this name of this compound is hydrogen peroxide. OF2, oxygen difluoride. The rules say that fluorine, when in a compound, is always -1. Now I've got 2 of those. And I've got an oxygen, and everything has to add up to 0 in a neutral compound. So -2 for my fluorines plus my oxygen oxidation number has to be 0. So my oxygen oxidation number has to be +2. How about that? So those are some examples of assigning oxidation numbers. This is an important skill to learn so that you can understand whether an oxidation or reduction is taking place in a reaction and know how to properly balance oxidation and reduction reactions. Thanks for watching both of these videos.